it would prove string theory was free of anomalies.
I do remember a particular moment when John Schwartz and I were talking at the blackboard and working out these numbers which had to fit, and they just had to match exactly. I remember joking with John Schwartz at that moment because there was thunder and lightning. There was a big mountainous storm in Aspen at that moment. And I remember saying something like, that we must be getting pretty close because the gods are trying to prevent us completing this calculation. And indeed, they did match.
The matching numbers meant the theory was free of anomalies, and it had the mathematical depth to encompass all four forces.
So we recognize not only that the strings could describe gravity, but they could also describe the other forces. So we spoke in terms of unification, and we saw this as a possibility of realizing the dream that Einstein had expressed in his later years of unifying the different forces in some deeper framework.
We felt great. That was an extraordinary moment because we realized that no other theory had ever succeeded in doing that.
But by now, it's like crying wolf. Each time we'd done something, I figured everyone's going to be excited. They weren't. So I figured, by now I didn't expect much of a reaction.
But this time, the reaction was explosive. In less than a year, the number of string theorists leapt from just a handful to hundreds.
Up to that moment, the longest talk I'd ever given on the subject was 5 minutes at some minor conference, and then suddenly I was invited all over the world to give talks and lectures and so forth.
String theory was christened the theory of everything. In early fall of 1984, I came here to Oxford University to begin my graduate studies in physics.
Some weeks after, I saw a poster for a lecture by Michael Green. I didn't know who he was, but then again, I really didn't know who anybody was. But the title of the lecture was something like The Theory of Everything, so how could I resist?
This elegant, new version of string theory seemed capable of describing all the building blocks of nature. Here's how. Inside every grain of sand are billions of tiny atoms. Every atom is made of smaller bits of matter, electrons orbiting a nucleus made of protons and neutrons, which are made of even smaller bits of matter called quarks. But string theory says this is not the end of the line. It makes the astounding claim that the particles making up everything in the universe are made of even smaller ingredients, tiny, wiggling strands of energy that look like strings. Each of these strings is unimaginably small. In fact, if an atom were enlarged to the size of the solar system, a string would only be as large as a tree. And here's the key idea. Just as different vibrational patterns or frequencies of a single cello string create what we hear as different musical notes, the different ways that strings vibrate give particles their unique properties, such as mass and charge. For example, the only difference between the particles making up you and me and the particles that transmit gravity and the other forces is the way these tiny strings vibrate. Composed of an enormous number of these oscillating strings, the universe can be thought of as a grand cosmic symphony. And this elegant idea resolves the conflict between our jittery, unpredictable picture of space on the subatomic scale and our smooth picture of space on the large scale. And it's the jitteriness of quantum theory versus the gentleness of Einstein's general theory of relativity that makes it so hard to bridge the two, to stitch them together. Now, what string theory does, it comes along and basically calms the jitters of quantum mechanics. It spreads them out by virtue of taking the old idea of a point particle and spreading it out into a string. So the jittery behavior is there, but it's just sufficiently less violent that quantum theory and general relativity stitch together perfectly within this framework. It's a triumph of mathematics. With nothing but these tiny, vibrating strands of energy, string theorists claim to be fulfilling Einstein's dream of uniting all forces and all matter. But this radical new theory contains a chink in its armor.
No experiment can ever check up what's going on at the distances that are being studied. No observation can relate to these tiny distances or high energies. That is to say, there ain't no experiment that could be done, nor is there any observation that could be made that would say, you guys are wrong. The theory is safe, permanently safe. Is that a theory of physics or a philosophy? I ask you.
People often criticize string theory for saying that it's very far removed from any direct experimental test, and surely it's not really a branch of physics for that reason. And my response to that is simply that they're going to be proved wrong.
Making string theory even harder to prove is that in order to work, the complex equations require something that sounds like it's straight out of science fiction. Extra dimensions of space.
We've always thought for centuries that there was only what we can see. You know, this dimension, that one, and another one. There's only 3 dimensions of space and 1 of time. And people who've said that there are extra dimensions of space have been labeled as, you know, crackpots or people who are bananas. Well, string theory really predicts it.
To be taken seriously, string theorists had to explain how this bizarre prediction could be true. And they claim that the far-out idea of extra dimensions may be more down to earth than you think. Let me show you what I mean. I'm off to see a guy who's one of the first people to think about this strange idea. I'm supposed to meet him at 4 o'clock at his apartment on 5th Avenue and 93rd Street on the 2nd floor. Now, in order to get to this meeting, I need 4 pieces of information. 1 for each of the 3 dimensions of space, a street, an avenue, and a floor number, and 1 more for time, the 4th dimension. You can think about these as the 4 dimensions of common experience. Left, right, back, forth, up, down, and time. As it turns out, the strange idea that there are additional dimensions stretches back almost a century. Our sense that we live in a universe of 3 spatial dimensions really seems beyond question. But in 1919, Theodor Kaluza, a virtually unknown German mathematician, had the courage to challenge the obvious. He suggested that maybe, just maybe, our universe has 1 more dimension that for some reason we just can't see.
Look, he says here, I like your idea. So why did he delay?
You see, Kaluza had sent his idea about an additional spatial dimension to Albert Einstein. And although Einstein was initially enthusiastic, he then seemed to waver and for 2 years held up publication of Kaluza's paper. Eventually, Kaluza's paper was published after Einstein decided extra dimensions were his cup of tea. Here's the idea. In 1916, Einstein showed that gravity is nothing but warps and ripples in the 4 familiar dimensions of space and time. Just 3 years later, Kaluza proposed that electromagnetism might also be ripples. But for that to be true, Kaluza needed a place for those ripples to occur. So Kaluza proposed an additional hidden dimension of space. But if Kaluza was right, where is this extra dimension? And what would extra dimensions look like? Can we even begin to imagine them? Well, building upon Kaluza's work,